So I'm going to discuss about stability and determinacy of structures. So it is required of you to determine first whether the structure is stable or unstable, and determinate or indeterminate. So that should be the automatic step before you analyze a structure. So a beam is said to be stable if to be determinate if the number of unknowns R, external reactions R, is equal to the number of available equations of statics. These equations are summation forces X, summation forces Y, and summation of moment about a point equals 0. So in general, N is the number of free body diagrams, and it is bounded by two pins or hinges. So if you can find compound structures, then the number of free body diagrams is indicative of its boundaries as two pins. So if there are n free body diagrams in general, then you multiply that by 3. So that would be the total number of equations of statics. So if r plus the number of the number of external reactions is or internal reactions is equal to r, and if it is equal to 3n, then we say that it is determinate. But it doesn't mean that it is stable, so it should also satisfy conditions of stability. So R is the number of unknowns of reactions and the number of parts of free body diagrams. So when R is equal to 3n and the structure is, or the beam, in this case beam, satisfies the conditions of stability, then we say that it is stable and statically stable and determinate. When R is greater than 3n, the beam is indeterminate, and it is stable also if it satisfies conditions of stability, which will be presented after this. Next is when R is less than 3n, then the system or the beam is a collapsible mechanism, so it is therefore unstable. So these are the different conditions of unstable structures. One, when all lines of actions or reactions are concurrent. So if they are concurrent, therefore the moment of the external loads cannot be balanced, counterbalanced, therefore it is unstable. So for instance, in this case, if these are the reactions rulers and the reactions are concurrent, they meet at this point here. Obviously, the sum of the moments or the moment sums about this point here, because these reactions are not involved, will be not zero, because obviously this external load will produce moment about that point of concurrency. So this beam will tend to rotate clockwise. So that's why it is unstable. Then second, if all lines of action are parallel to each other, then it is unstable. So this one is unstable. I think you have seen this in reality. This is used as a platform for those who are cleaning the walls of buildings, or when painters, uh, this is the structure where painters stand and paint the outer walls of the building. So when there is a lateral load or lateral force like earthquake or wind, this will sway. So that makes it unstable because all lines of actions or reactions are parallel, even if it is indeterminate, because there are 5 unknown tensions or reactions, but it is still unstable. So these criteria for unstable structures are also applicable for beams. Even this criteria here, that 3 criteria, but frames have their specific criteria also, but as I said, you can still use this criteria for beams. For trusses, the following are the criteria. Remember that the total number of unknowns for a truss would be number of reactions. Reactions are unknowns, plus the number of bar elements. Each bar represents an unknown because the only unknown of a bar is the force of the bar or the stress of the bar. And the reaction or the direction is already known. It is directed along the axis of the truss member. Remember that a truss member is a two-force body. So it is either tension or compression. So this number of unknowns should be balanced by the total number of static equations. And if you remember the method of joints, at each joint you can formulate two equations, two static equations or equilibrium equations for a truss joint. That is summation forces x equals 0 and summation forces along y equals 0. So the total number of equations therefore is equal to 2 times j, where j is the number of joints. So R for the number of external reactions, D for the number of bars in a truss. That's the total number of unknowns. If it is equal to 3 times the number of joints, then it is statically determinate and stable. However, it should also follow geometric stable conditions or requirements and some internal requirements which will be presented after this discussion. So when the number of reactions plus bars is equal to 2j, this is for a 2D truss, you just replace 2 by 3 for a 3D truss, then you follow the same criteria. Then the truss is said to be statically determinate and stable as long as it is both externally and internally stable. So the cases for internal and external stabilities will be presented after these three criteria. R is the number of support reactions, and B is the number of bars or bar members, and J is the number of joints. When R plus B is greater than 2J and the truss is stable in general, so the truss is statically stable and indeterminate, then you define the degree of indeterminacy by getting the difference of R plus B and 2J. So if R plus B is 11, for example, and 2J is 10, so the truss is said to be statically stable and indeterminate to the first degree. So again, the degree of indeterminacy is the difference of these two terms, two numbers in the left and in the right. Then when R plus B is less than 2J, it is a collapsible mechanism again, so it is unstable. By the way, just like in this equation in number 2, so this is supposedly statically indeterminate, but because it is unstable, so therefore we conclude that it is unstable. It is immaterial anymore to state if it is indeterminate to certain degree, because on the first place it is already unstable. So there's no place for unstable structures in civil engineering field. Do you allow unstable structures in the civil engineering field? That will be a disaster of our course. So that's why we reject structures that are unstable. So because they are unstable, it is immaterial or not important anymore to specify the degree of indeterminacy for unstable structures. So for a 3D truss, the criterion, as I said, you just replace 2 by 3. And the same definition for these terms R, B, and J apply. So these are the cases of unstable trusses. One case is when the external reactions meet at a point. So it is called unstable externally. Like this truss here, it is supported by these short links. And remember that for short links, the direction of the reactions will be along the link, along the axis of the link. So these are the reactions, and the reactions meet at that point there. So summation of moment at this point is not balanced or is not zero, because definitely if we have an external load, there is moment about that joint. It will cause the truss to somewhat rotate clockwise because of the moment of the external load, and this is not balanced by the external reaction. So that is an unstable truss. Then this one is an example of a truss, even if there are supports here that are pins. If 3 pins or hinges are on the straight line, so it will be unstable, it will collapse definitely. Have you seen a bridge like that? So it seems that something is missing. And for this truss to be stable, you need an additional bar here, because if there's no additional bar here, the truss will collapse in this manner. So this will be the line, imaginary line for the possible collapse of this truss when loaded. So this is missing. For this to be stable, so you should add that member there to resist compression. Then unstable internally, this is the situation where it's somewhat difficult to find out, but you really need experience for this unstable internally. So this happens when you section members and the members meet at a point. So for example, this truss here, this is unstable internally because when you section these members here, these 3 members, and you consider the upper portion of that section, then obviously summation of moment at their meeting point is not zero. So it is not zero because if there is a load here, there is moment of this load about 0.0, and no one of the members of this truss will counter the moment produced by this force P here, because all the 3 unknown members meet there. So their moments about this point here would be zero, but the moment of the external load is not zero. So that's why this is unstable internally. Then for frames, so this is a frame. So we must define about elements of a frame like the joints. So the joints are these indicated points here, the intersection between 2 or more members, but this external joint here is also a joint, considered a joint, except for this. So these are joints, that one, these are joints, joints, joint, joint, joint. This one is not a joint, that is an internal pin, but there is one condition here. The number of condition here is 1. And what is that condition that we know about? The moment about a pin is 0, right? So these 2 members tend to rotate about this pin here. So we know that the moment there is 0. Now, how about the pin at the joint? So for a pin at a joint, there will be 3 conditions there. So in general, for a pin at a joint, the number of conditions is defined as the number of meeting members. In this case, there are 4 meeting members at this joint here, minus 1. So that's the formula for determining the number of conditions for a joint with more than 2 members connected to that joint. So, by the way, this overhanging member or cantilever members are not counted as bars in the criteria. So, take note of that. So, that is defined as 1 bar. These are not bars. So, B is the number of bars. This would be the criterion. R would be the number of external reactions. B is the number of bars, and remember that in each bar there are 3 unknowns for a 2D frame. The unknowns are the axial force, the shear force and the moment. So therefore, in each bar, there will be three unknowns: shear, axial, and moment. So you multiply the number of bars by 3. That would be the number of unknowns for the forces, internal forces of a bar. So the total number of unknowns therefore would be external reactions, number of external reactions plus 3 times number of bars. Then how many equations can be set up? Equations or number of static equations that can be set up. The number of static equations that can be set up is equal to, so if you count the number of joints, at each joint there are also 3 equations of statics that can be set up. These are summation forces along the axis of the bar equals 0. So meaning to say, summation forces along the axis of the bar equals 0. That's 1. Summation forces perpendicular to the axis of the bar for shear equals 0. And third, summation of moment about any point on the bar equals 0. So there are 3 equations also per joint of a frame. And you add the known information about the number of conditions. So therefore, the criterion is R plus 3 times B should be equal to 3 times J plus C. So that would be the criterion. R plus 3 times bar should be equal to 3 times joints, number of joints plus C. So if this equation is satisfied, then we say that the frame is stable and determinate. In general, frames are highly indeterminate. So of course, if there is unstable frame, that would be with respect to internal, perhaps a portion of the frame which is a beam or a column which is unstable, but for a whole frame it is a stable structure. So it is, we can safely say that all frames are building frames are stable and indeterminate. So the degree of indeterminacy again is determined by the difference of 3B plus R and 3J plus C. So C is number of conditions, which is defined earlier as the number of members meeting at the internal hinge minus 1. So let's have this example. Determine whether the structure is stable or unstable, and determinate or indeterminate. If indeterminate, specify the degree of indeterminacy. So first, before you count the number of reactions, you have to test the structure if it is stable. For instance, if we apply a horizontal force, let's say going to the left, is there a component of the reaction which will resist that horizontal active force? So try to answer that question. So there is, because we have a pin here, which is also connected to this pin here. So the pin has 2 unknown reaction components, vertical and horizontal. So there is no movement leftward. How about rightward? There is also no movement rightward because of the horizontal component of the action of this pin here. Next is upward force. If you push this, will it rotate this way? Can it rotate that way? So if you push this upward, so there is a force that will develop here. This will also push this member upward, and this cannot move upward because of the vertical component of the reactions of these 2 supports here. So it cannot rotate clockwise or counterclockwise. Same is true if you apply downward force. It cannot rotate because the vertical component of force that is transmitted to this will prevent the truss from the beam from rotating or collapsing. So now we have decided that it is stable. So count the number of reactions. 2, 2 here, 1 here because it is a ruler, 2 here, another 2, 1 and 2. Then 2, 4, 5, 7, 9, 10, 12. R is 12. Then number of free body diagrams, this is the first, this is the second, hinge to hinge, third, and fourth. So therefore, n is 4, and therefore 12 is equal to 3 times 4. And because the structure is stable, therefore it is statically stable and determinate. Second, this is a truss. You count the number of bars, the number of reactions first is 3, the number of bars is 27. I leave the counting to you. You just count the number of bars. R is 3. Then joints, you count it. There are 15 joints. Then 3 plus 27 is 30 equals 2 times 15. And you experience this type of truss. This is a pink truss, and a pink truss is stable. So therefore, this is statically stable and determinate. Next, we have a truss, a cantilevered truss. We have two unknown reactions here. So R is 4 for this case. So R is 4. The number of bars is 15. I leave the counting to you. So this is a joint. So bars is 15. Joints is 2, 4, 6, 8. 8 joints. Then 4 plus 15 is 19. And 19 is greater than 2 times number of joints, which is 8. So therefore, the truss is stable and indeterminate, statically stable and indeterminate to the third degree, because 19 minus 16 is 3. Next, this is obviously an unstable truss internally, because you cannot find diagonals here that which will resist lateral forces or horizontal forces. So therefore, this is unstable, and it is immaterial to state the degree of indeterminacy, or whether whether R plus bars is greater or less than 2J. This is a frame. So obviously, by taking a closer look, we have a stable frame. There are two unknowns here. There are 3 reactions here, 3 also here, then 1 here. Then there is one condition here, which is C is 1. And remember, this is only 1 bar, as in our guide here. So the number of bars is 1, 2, 3, 4, 5. 5 bars. And the number of joints is 1, 2, 3, 4, 5. 5 joints. 5 bars and 5 joints. So R plus 3 times 5 is greater, condition is 1. R plus 3 times B, which is 5, is greater than 3 times J, which is 6 plus 1. 24 is greater than 19. So 24 minus 19 is 5. Therefore, this is statically stable and indeterminate to the 5th degree. This is another frame. We have 3, 3, 3 here as number of reactions. So it's 9. There are 4 conditions, and the number of bars is 2, 4, 6, 8, 10. 10 bars. And joints is 1, 2, 3, 3, 6, 9. 9 joints. Then 9 plus 3 times 10 is greater than 3 times 9 plus conditions 4. So 39 is greater than 27 plus 4, 31. 39 minus 31 is 8. So the frame is statically indeterminate, statically stable and indeterminate to the 8th degree. Then this one is a truss. There are 4 reactions. Number of bars, you just count. This is not a joint, so there are only 2 members for this case. So bars is 8. Joints is 5. Then 4 plus 8 is greater than 2 times j, which is 5. So 12 is greater than 10. So this is statically stable and indeterminate to the second degree na truss. Then this one is a beam. Before counting, as I said, we look at closely for a possible collapse of this continuous beam. So definitely, because these are pins, the members tend to rotate about the pin. There are no resistances about a pin. So therefore, this is unstable. Even if you count the number of reactions, number of free body diagrams, it will lead you to indeterminate structure. But even if it is indeterminate, it is not stable because this portion will collapse definitely when there is a load here. And this will be the possible geometrical figure for possible collapse when there is a load somewhere in this portion. So that's unstable automatically. This one also is unstable. You do not count the number of reactions by taking a cursory look. Remember that this is a roller. When a load is placed here, this tends to rotate this way, like that, because these are all pins. And also, when there is a load here, it will geometrically collapse by this geometric configuration. So that is unstable also. This is one possible failure or collapse of this beam. This is the other possibility. So that is unstable. Then this is a frame. R is 3 here. 2, 2, 2. The number of bars is 2, 4, 6, 8. Remember, you do not consider this. 8, 10, 12, 14. So bars is 14. Joints is 3, 6, 9, 12. 12 joints. So 10 plus 3 times 14 is 52. Position is 0, by the way. Is greater than 3 times joint is 36. 52 is greater than 36. So therefore, the frame is statically stable and indeterminate to the 16th degree. So that's it. That's all.